guys, welcome to Learn Extra Live. Today we are doing physical science, guys, for grade 11s. I hope you grade 11s are excited as I am, of course, for an awesome lesson. What we need to do today is that you guys need to jump onto our Facebook page, which is facebook.com/learnextra, and our Twitter handle is @learnextra. You guys need to ask as many questions as you can. Say as many things as you can, basically, guys, because nothing that you say will ever go unnoticed. I promise you, I'm seated here the entire lesson and I'm willing to answer every single one of your questions. Today we're with Tracy and we're doing atomic combinations, guys. So get out your worksheets and your workbooks and your textbooks and your pens and pencils, and also jump on to learnextralive.co.za/live for the notes that Tracy will be working off today, guys. Isn't that absolutely special? I know it is. Don't worry, don't shout at the screen. I've got you. Jump onto that page, download them. You can highlight them, you can share them with your friends, your uncles, if they're doing grade 11 physical science, and your cousins and your friends, guys. It's going to be an awesome show, basically. So please join me on the page and join Tracy for such an awesome lesson. How are you, Tracy?
Good, and you?
Good, thank you.
I like that let's share with your uncle.
I think your uncles need some atomic combinations.
Hey, why not? Anyway, as Katlego said, we're doing atomic combinations today, and we're looking at molecular structure, and we are going to cover a lot of work today. So hold on to your seats, and I have got some fun stuff planned for near the end. We're going to make some things with marshmallows, which are all mine. Anyway, so we're going to look at atomic combinations. What are we actually going to try to get through today? Well, we're going to identify and describe the shape of molecules. That's really important. We're going to discuss the concept of intermolecular forces. This is a very new concept for you guys. And then we're going to discuss how intermolecular forces affect the physical properties of substances, okay? So now remember, physical properties are things like boiling point, melting point, all those sort of things. You spent a lot of time at the beginning of grade 10 discussing those things. And what we're going to look at is what actually determines those boiling points and melting points, and we're going to look at some trends, okay? So the first thing we need to do is let's go back and recap on some of the different types of chemical bonds. Now, chemical bonds are what we call intramolecular bonds, okay? So this, what we're doing first is intra, okay, with an A, not intramolecular bonds. So what we're discussing for this first little bit is the bonds between the atoms, okay? So how the electrons are shared or given, or how they react with each other. It's the sharing or the giving of electrons. Now, the first one is your covalent bond. Okay, covalent bond, this is really what we get into with shapes today. When two non-metals, or two or more non-metals, okay, bond together in a covalent bond, we get a bond together, it's a covalent bond, okay? What is it characterized? The electrons are shared between the two atoms. The electrons are shared between the between the atoms. Remember, the whole point of bonding is for our atoms to get a complete energy level. So if we look at something like chlorine, okay, and you remember from grade 10, you did Lewis notation. Remember, chlorine is in group 7. Okay, chlorine looks like this, has 7 valence electrons, and we go, well, over here, it has an empty space. In order for chlorine to get a full energy level, it needs another electron. If we bring along another chlorine, okay, this chlorine also has 7 valence electrons, and it also has an open space. So now what happens is these, let me just get rid of, where did it go? I just want to get rid of this part quickly. Now, what happens is these two electrons come together and say, well, we can share this space. Both chlorines want an electron really, really badly, but because they have the same electronegativity, in other words, they have the same force of attraction for that bond, for those electrons, they will share them, okay? So this becomes a shared pair. In this case, it's what we call a non-polar bond. All right, do you remember that from last year? It's completely equal sharing, non-polar, okay, which means neither of them tend to have the electron more than the other. If we look at hydrogen chloride, HCl. Remember, hydrogen only has one little electron, which it doesn't really want to give away. And then we have chlorine, okay, which has 7. So what happens is it'll bond like this. Remember this? Here's our bonding pair. That's what we call that. It's called a bonding pair. But there's not equal sharing. Now there's very unequal sharing. Chlorine actually has a high electronegativity. Remember that from last year? Electronegativity being the force of attraction for the bonding pair. Chlorine wants that electron so badly that what happens is this becomes what we call a polar bond. Okay? It's a polar bond. So the chlorine almost looks negative and the hydrogen almost looks positive, but not quite. We don't say it's become an ion, so the hydrogen hasn't given its electron away, but because the electrons that are shared between the hydrogen and chlorine are spent so much time with the chlorine starts to look slightly negative. So that becomes polar. So with non-polar, completely equal sharing. With polar, not so much. One atom tends to take the electrons more than the other, and it all depends on the electronegativity. So the atom with a higher electronegativity tends to look a little bit negative. Then we get ionic bonds, okay? Now, ionic bonds are between a non-metal and a metal. What are these characterized by? Well, your ionic bonds are characterized by the fact that there is a transfer of electrons, okay? So the metal will give away its electrons, okay? And then they get stuck together by electrostatic forces. It's a very, very strong bond, okay? Because it's an electrostatic force. It's not just a slight attraction. It's a very strong bond. It's also why ionic solids tend to be what we call brittle. They will shatter rather than bend or break, okay? Now, an example of this would be something like sodium chloride. Sodium is in the first group, so sodium has one lone little electron in its valence shell, okay, and its outer shell has one valence electron. Chlorine comes along, and chlorine, like we've said already, has 7, okay, and now we've got to say to ourselves, all right, the point of bonding is to get a complete outer energy level because they want to look like the noble gases. Sodium looks at this and goes, okay, well, you know, I've got lots of other electrons and atoms and stuff, and sodium's not so fond of its electrons. So it goes, well, you know what, chlorine, you can have my electron. Chlorine goes, yay, I'm very happy. But what does that mean? That means that the sodium becomes positively charged because it lost an electron, and the chlorine, if we keep the Lewis notation, okay, has gained that extra electron and is now negatively charged. So the chlorine and the sodium come together and we have positive and negative ions, charged particles that are coming together, electrostatic charges. It also means that when we look at the structure of an ionic solid, it has a crystal structure. It's a very regular structure. That's all the things you can do. I'm hoping somewhere in primary school you grew crystals, sugar crystals, salt crystals, maybe some copper sulfate crystals, and you get those beautiful nice structures. That's because they are ionic. And as much as we write the formula for sodium chloride as NaCl, you actually would be extremely hard-pressed to be able to isolate a single sodium and chlorine set together. It's actually called a formula unit. You find millions of them together, okay? Ionic solids, not that important in terms of shape because they make nice crystal structures. We get these charged ions. Then the last one you would have done is metallic bonding, okay? Which is the easiest to remember out of all of them because it's exactly what its name says. It's between metals. Either just metals in its atom form or when we have alloys. So even steel, which is more a mixture of metals than an actual bond between metals, it's the same thing. Now, what is this characterized by? The fact that we have, sorry if it's gone too far, a positive atomic core. Sometimes that's called a positive kernel. It all depends on which book you're using. Surrounded by a sea of delocalized electrons. Essentially, the metals are going, you know what? As long as I can see enough electrons around the inner shell for me to be neutral, I don't actually care where they come from. So if we could take a microscope and look at what the inside of a metal would look like, we would have positive kernels. Now, these positive kernels are not just the nucleus, okay? They're the nucleus plus the inner filled energy shells, because remember, as you go down the periodic table, you get a new energy level. So it's the inner filled energy levels, okay? And I'd take me, see, so we've got these, and they're regular. Now, these positive kernels, which those are pluses, not fours, backwards, these positive kernels are set in place, okay? They're not going to move. You're not going to get them going all over the place, because what happens is now we have a sea of electrons. So all the electrons needed, so all the valency electrons are free to move, because it's almost like the valence shells overlap each other. So these valence electrons are free to move, and this is why metals are such good conductors, because when I give those electrons energy by putting it into a circuit, adding it to a battery, okay, these electrons get enough energy and they can move from one place to another. That's why they're such good conductors, okay? Positive kernel, sea of electrons. Now, what's really important here is we're going to need to look at covalent molecules in detail, because they're the ones that are a little bit more complicated. Think about the fact that you would have been taught up till now, things like, you know that water looks like Mickey Mouse ears when you draw it. In grade 9, you probably would have done a thing called dot molecules. You draw it as a molecule, and you draw an hydrogen with an oxygen with two little hydrogen, looks like Mickey Mouse ears, okay? And I'm pretty sure some of you have gone, but why? Well, pretty much your teacher probably went, because it is, just learn it. I mean, I do that with my grade 9s too. But now you're in grade 11, so that means now you need to be able to explain it. So what we're going to do is we're going to take a break, but when we come back from the break, we're going to deal with what's known as VESPA, valence shell electron pair repulsion theory. This is so important. I really hope you've downloaded the notes. If not, make sure, as you get told all the time, to make sure you got a piece of paper and a pen, because I'm going to be explaining it. I've got marshmallows and balloons and all sorts of things. So we're going to take a break.
Before we take that break,
okay,
Tracy,
yes.
There's a question by Simakaleng Smacks as well as
okay.
Orki.
Okay, as long as I'm not having to repeat those
Don't
names.
worry.
But thank you. Anyway,
they are
yes.
both asking, what is dative covalent bond?
Okay. Dative covalent bond is where we get a slightly different version. I'm going to do it really quickly. Let me go back to the covalent. Dative covalent, in a normal covalent bond, okay, it's actually a really good question. Okay. In a normal covalent bond, both atoms involved in the covalent bond contribute to the electron pair. However, in dative covalent bonds, the ones you're going to use means that you've got a little hydrogen that's come along, and this poor little hydrogen is now what we call a naked hydrogen. Poor thing, okay?
Poor thingy.
Yeah. Why is it called a naked? It's actually a naked proton, because this hydrogen, somewhere along its travels, has lost its electron, so it's a positive ion. If it, say, comes now and is reacted with ammonia, NH3, okay, which looks like this when we draw its bonding, okay? Now what happens, and for most of our dative covalent bonding, results in a charged particle. So you only got a couple, you're going to have to do H3O plus and NH4 plus. This hydrogen comes along to the NH4 and goes, NH3 and goes, hello, Mr. Nitrogen. Okay, they don't really talk to each other. Please just remember that. Don't write this in a test or exam. But this hydrogen comes along with an empty orbital. It goes here and it says, well, here's what we call a lone pair. A pair of electrons that aren't bonded to everything. And the hydrogen attaches itself to this lone pair. So what happens is the nitrogen, which looked like this, the ammonia, sorry. So that was the ammonia originally. That's 2 electrons. And along comes this extra hydrogen and attaches it to itself to the top. But this hydrogen contributed nothing to this shared pair. Nothing. So it's not a true shared pair of electrons, because it's not a case of both contributed, which is what normally happens. Only one atom contributed, and it also results in the ion becoming positive. So a dative covalent bond is when you have a shared pair of electrons which is only being contributed by one of the atoms involved, okay? And normally ends up being a positive ion. And the ones you're going to get asked most are NH4 plus, like I've done now, and it's probably a good idea to see if you can work out how H3O plus would work. Okay.
Thank you, Tracy.
I hope that helps.
I think it does.
Cool.
So guys, we're going to go for a really quick ad break. As Tracy said, make sure that you download those notes. If you cannot and you probably don't have a computer in front of you, that's okay. That pen and paper, guys, keep writing. This stuff is so important and it will carry you for years. So make sure that you're jotting it down. See you right after the break. Welcome back, Mindsetters. What an awesome show it's been. We are doing physical science, and the studio, guys, the energy is so amazing, guys. There's such awesome things that you guys are going to see. I hope that by now you have spoken to everyone that you know in your schools, out of your schools, to watch the show, guys. The stuff is really, really important. And if they perhaps cannot watch it, be a mate and send it through to them, guys, or tell us where to join us. And that's, of course, facebook.com/learnextra or @learnextra for Twitter. And tell them that they can also download notes, guys. That is, someone said that I said it slowly, Tracy. I mean fast.
Fast. You did it, but it's okay.
Mama
They're grade 11s. They're very fast.
So can you say it for them? Do you remember it?
Learn Extra Live.
No, I'll say it for you guys.
Okay, fine.
learnextra.co.za/live. And I've posted the fast link on the page. So you don't even need to remember that. You just need to click on it and it will take you right there. Over to you, Tracy.
And it's such a cool website. Guys,
awesome.
You know it. It is so worth going to the website. Not only for the physical science, obviously, but for the maths and the maths lit and the accounting and business and everything. And, just keep getting stuff, even for next year. It's always good to keep these things in place. And yes, I do have a pair of balloons in my hand. And hopefully I won't go popping any balloons in the next little while.
That's okay. We can have a party with them.
Yeah, and our producer's wanting something fun to happen. Anyway, so we now need to look at shapes. Now, guys, this one really is, we're not going to spend too much time talking about the real nitty-gritty of it. I want you to get to the basic shapes, and there are really only about 4 or 5 real basic shapes that you need to be able to identify. And all of these have to do with covalent bindings. This is not ionic, this is not metallic, this is covalent. Right now, I'm also not concerned about whether the bond is polar or non-polar, okay? Now, the first shape is actually the simplest out of all of them, because there's only 2 atoms involved, like HCl. It's linear, it's straight. So this is what my 2 little balloons who are busy deflating, trying to show you, okay? It's linear, okay? They've got no other way but to be straight. Or, which is why everyone at the moment is not liking me in the studio, is we can use, and I've used 2 marshmallows to show you, okay? Is we're going to have a party afterwards. When they're linear like this, they can only be in one shape. And also means that between these is only one bonding pair, okay? One bonding pair of electrons. So remember, with HCl, if we have to draw, now I haven't put it in here, but if we have to draw the dot molecule, the Lewis notation, okay, we would find that we have one pair of electrons in the middle. I'm not doing all the ones around the side, okay? Makes it nice and linear, straight line, nice and easy to remember. But what happens, okay, when, wait, I've got to put it in that one. Ooh, and now it's locked. That doesn't help me. Unlock. Sorry, I'm not having a good day with these things. Okay, when we get to a 4 bonding pairs, now we get another linear shape, which I couldn't actually make with my balloons, but I did with the marshmallows, okay? So this is carbon dioxide. Now what happens is this is also linear. I have got 3 atoms now. There is an option, it doesn't have to be a straight line. It all depends on the arrangement of the electrons, okay? Now what's special about this is there are no what we call lone pairs. So if we have to draw the Lewis notation for CO2, okay, the lone pairs on CO2, because we actually have the double bond between the carbon and the oxygen, and it does this, okay? Now, electrons are a little like you and your siblings. They want their own space, okay? And heaven forbid somebody come into their space. They like to take up as much space as they like, as they can. They have personal space issues. You all know friends like
I know
that.
what it feels like, don't
Well,
worry.
I have a friend at school, at work. It's actually quite funny. I sit down, she moves over like she's my best friend, but it's a personal space issue, and we all
So
have
she has like a
those.
personal like bubble.
Yeah, it's a
around
personal
her.
bubble thing.
Okay.
And electrons are the same, okay? They like a big personal space, okay? So they're going to take up as much room as they can. So first of all, there's nothing here at the top here that's going to take up extra space, but the electrons on the outside are going to, how can we get as far away as possible? So they stretch out, okay? This is linear, but not all are going to be linear in shape. So what happens when this changes and we have something like water, H2O, okay, which I also couldn't show with my balloons. I'm going to get back to my balloons in a second. So H2O, now we have two bonding pairs, and I said there we also have two lone pairs. If I draw the Lewis notation diagram for water, okay, water is H2O, so H, and then the oxygen does this, and there's the O, okay? Now, I did actually make this out of marshmallows. So there's my oxygen in the middle. This is so not to scale, just so you know. Oxygen sitting in the middle, and here's my two hydrogens. The oxygen has two lone pairs. Those electrons that are sitting over here at the top there are going, need space, need space. The only way they can have space is by pushing the hydrogens away from them, okay? So these top electrons, these here, they push the hydrogen away from it. If those lone pairs didn't exist, this would be straight, like carbon dioxide, okay? But because the lone pairs sitting on the top here going, we want our own space, they don't like sharing, they push the hydrogen away, and they become what we call bent or angular, and I think I put it as angular. Sometimes this is also called a bent, ooh, that's not even vaguely, that's even worse. Okay, should I try write this so you can read it? How's that sound? Bent. See, look, I can write neatly on the board. Okay, so it's a bent because it's not straight. It's bent, okay? But that's with 3. We get another shape, which I didn't put in the notes, but I want you to see it, which I can show you really nicely with my balloons, which is called trigonal planar, okay? Now, this is a very special molecule. This one, which you're going to see often, is known as, for example, BF3. Boron sits in group 3, or 13 on the new periodic table, and is actually represented in the middle here. This is a flat molecule. I need you to see this, okay? That this sits, it's planar, it's flat, okay? It's trigonal because it almost looks like a triangle. This has no lone pairs, okay? Boron only has 3 valence electrons, which fluorine then comes along and bonds to. There is no lone pair. There's no electrons going, no, actually I want some space. It doesn't need any space. So it makes this really nice, flat molecule, okay? Nice and flat, okay? Which is great. We like these. But if we now go on to the next one that I want to look at, which is what something like ammonia is, okay? Ammonia comes along, and ammonia also is NH3. So we have BF3, okay, no lone pairs. Ammonia, which is, maybe I should choose a pen, which is NH3. Now, we just discussed ammonia because we did it with the dates of covalent bonding. Ammonia comes along and we go, okay, here we go. Oh, no, maybe I should do what I'm doing. There we go, NH3. And we go, hang on, wait, there's a problem. Biggest difference between BF3 and NH3 is NH3 has an extra set of has an extra pair of electrons. So, what that means is it forms, okay, I'll use that one in a second. It actually forms this shape, which is known as pyramidal, okay? Because despite my really badly constructed marshmallow molecule, it looks like a pyramid, stands up like a pyramid. Over here, that lone pair of electrons is really important because if we go back to my balloons, this orange one here represents my lone pair of electrons. It comes along. This would be a flat molecule, but it goes, no, 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 no. I want space. And because it wants space, and I'm not doing so well here, it pushes the others away from it, okay? And these now form the pyramidal shape that I was looking at, okay? Because this pair of electrons, this is my lone pair, is pushing down on them. They need to go as far away as they possibly can. The only way that happens is to make like a pyramid shape, okay? And that must be the worst sound in the world, playing with the balloons. But it makes this nice.
Yeah.
I'm going to put them down before I pop something and give myself a fright, and that would be scary. So those electrons, which I'll highlight for you, push down, and they make it go as far away as possible, okay? So we get our pyramidal shape. The next one, it's actually probably my favorite, is what happens when we have something like CH4, okay? So now let's think. We've done pyramidal, planar, all the rest of it. Now we go to CH4 and we go, okay, for example, CH4. So if we have to draw the Lewis notation for methane, which is what CH4 is, okay, here we go. This is an H. Okay, and we go, ooh, okay, well, first of all, no lone pairs. Yay, very excited. Everyone's very happy. And we go, okay, well, maybe this is going to be flat. Maybe. But remember, the point is that each of the atoms want to be as far away from each other as they possibly can, because the model we're working with is called the valence shell electron pair repulsion theory, VESPA for short. That means the electrons, the atoms, want to be as far away from each other as possible. So what happens is it does this, without me falling through my platform. It does this. Now this isn't flat, okay? And it's not really at 90 degrees either. So it's not like a nice little pyramid, but we get this shape. This is known as a tetrahedral shape. Okay, my balloons are starting to deflate already. Anyway, it's tetrahedral. So it's almost like my pyramidal, but it's got an extra piece at the top. So when we look at it, if we do it as a diagram, and I'm going to fall through the hole in my platform just now. Anyway, so this is tetrahedral, 4 bonding pairs, okay? 4 bonding pairs, no lone pairs, okay? 4 pairs that sit together, they shared nicely. Please note, with all of these, I have not once mentioned polar or non-polar, okay? Not once, though that is important. The shape of these molecules is going to determine whether the molecule is polar. This molecule, tetrahedral, okay, and I'm just going to give you a bit of a way to think about it. The bond between carbon and hydrogen, most definitely polar. The carbon, ooh, I've done all sorts of weird and wonderful things on there. There we go. I'm having one of those days. The carbon, so the carbon's sitting in the middle. The bond between carbon and hydrogen polar, okay? Carbon likes the electron more than hydrogen does, so carbon looks slightly negative. Each of these hydrogens look slightly positive. So now we look and we go, but polar means I must have a positive side and a negative side. So if I look at my molecule and I look at the shape and I go, okay, positive, 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 positive. The negative sits in the middle. This molecule acts as if it's non-polar, okay? So the bond between the carbon and the hydrogen is polar, unequal sharing. There's nothing we can do about that. But the molecule is non-polar, okay? Very important. For our linear ones, for the straight across, if it's a non-polar bond, it's a non-polar molecule. If it is a polar bond like hydrogen chloride, It is a polar molecule. For linear, okay, the one that's straight across, if we look back at my marshmallows, carbon and oxygen, and I can't remember which one it is. I think the oxygen is slightly negative. You can't find a positive negative side, because if the top part, if the side, those two atoms are the same, say they're negative, the middle one's positive, the middle's positive. So I can't actually find a positive and negative side. It's actually a very symmetrical molecule. This is non-polar. Angular, absolutely is it polar, if it's a polar bond. Okay? If the bond between the two atoms is non-polar, then the molecule's non-polar. And it's easy to see here. This would be, if this is water, then this side is slightly negative, sorry, because that's the oxygens. That side is slightly positive. I can find a positive negative side, okay? With my tetrahedral, with my pyramidal, this one's actually the easiest to see, those are my electrons. Those are probably going to be positively charged, okay? Positive side, negative side, polar molecule. Positive side, negative side, polar molecule, okay? Tetrahedral, absolutely going to be nonpolar, but we just discussed that. Why is this important? Because whether the molecule is polar or not has an effect on the intermolecular forces, which is what we're going to need to discuss next, okay? So the shape now determines whether the molecule is polar or nonpolar. That has a direct influence on the intermolecular forces, which then has a direct influence on the physical properties, okay? So I'm going to leave you hanging on that little tidbit, because when we come back, we're going to talk about intermolecular forces, and I have some fun things to show you.
I like fun, and I'm sure every one of you loves fun as well. So make sure that you join us after this break. In fact, for this break, do not move off those seats, guys. We will be right back. Welcome back, Mindsetters. As you know, you are currently in a physical science lesson. It's been so awesome so far, and I know that you guys think so because you've said so on the page. And I want you to keep chatting, guys. Keep chatting to each other. Keep chatting to me. Just speak your mind, guys. Ask any questions. Most importantly, ask questions, guys. Make sure that by the end of the show, you understand what exactly it is that this section of science wants from you. And you guys need to actually extract that knowledge from us by either joining us on Facebook or downloading the notes or even jumping onto YouTube, guys. This is so important, and I hope that you guys have seen on the page, because I've put it up, that on our YouTube page, that is www.youtube.com/mindsetlearn, you stand a chance to watch. Actually, it's not even a chance, because you actually can just click on it and watch it. To watch all our shows, guys. So in case you've missed this one or you missed the beginning, don't you worry. You can just jump onto YouTube and watch the shows directly. Over to you, Tracy.
Excellent on the small screen as well as the big screen. Anyway, moving on. So, at the end, in the last section, we were going through the different shapes, and I said now we're going to look at intermolecular forces. Okay, now the difference is, look here, this is wrong way around. Inter means between. So now we've got to discuss what actually keeps the molecules and atoms together, because remember, you've done in grade 10, you did solid, liquids, and gases, and you said, well, when solids are close together, the forces of attraction are quite strong, and they vibrate in place, and when they're liquids, they're not so strong. But what is that force? Where does it come from? And this is the intermolecular forces. Now, the intermolecular forces are basically the forces that keep molecules together in solid, liquid, or gas phase. They are very specifically called van der Waals forces. That's just the name we give to them. The strength of these forces determines physical properties like boiling point, melting point, viscosity, surface tension, and density. So it's all important things what these van der Waals forces determine. Molecules that are polar in nature have stronger van der Waals forces than ones that are non-polar. Okay, so the stronger the force is, the harder it is, the more energy needed to break the molecules away from each other. All right? The stronger the force, the more energy needed. But now before we go and look at an experiment and a demonstration of stuff, let's define some of these physical properties, because that's really important that you get this, because I might talk about boiling point, but if you don't know what we mean by that, then it doesn't make any sense, okay? So here are some of the definitions. Boiling point, the temperature at which the vapor pressure is equal to atmospheric pressure. It's the temperature at which it turns into a gas, basically. But it's the point where you have your molecules have enough energy to escape from the liquid and become a gas. And then they form a pressure. If it's equal to atmospheric pressure, then the liquid boils. Melting point is the temperature when it becomes a liquid. That's pretty self-explanatory. Viscosity, which is actually what we're going to look at in detail today, is an indication of a liquid's resistance to flow. So this is an indication of how easily it moves over each other or itself, okay? Surface tension is the cohesive forces. Cohesive is the intermolecular forces, essentially, that on the surface of a volume of liquid, like on water. It's also what makes liquid flat, okay? And density, which is spelled very strangely, let's just take that out, is the number of particles per unit volume. You hopefully did a lot of stuff in grade 9 on density. Now, we are going to do a little bit of a demonstration. And this really is just to show you. We're not going to take any measurements, but we're going to go over to the table in a second, and the first thing we're going to do, actually we're going to go now, so let's go over to the table. Ooh, without me destroying the board. Okay. And the first thing we're going to do is we're going to take some carbon dioxide. Now, carbon dioxide is dry ice. It's what those wonderful ice cream men have with them, okay? And it's what keeps their ice cream nice and cold. Now, I'm not going, please excuse the really big gloves, but I don't really want to kill my hands. But what we have is in this cooler box, okay, I'm just going to tip it over like this a little bit, is we have quite a bit of dry ice, okay? It's a nice big chunk, and hopefully you can see we've opened the cooler box and you can see like a smoke coming off. It's what they use in gas in smoke machines, okay, on stages and stuff. Now the nice thing is here, what we've had for a while in this beaker is we've got a piece of dry ice, and hopefully our wonderful friend Wilson can actually really get in quite close over here, and you can see all the, in fact, the moisture in the air has frozen on the side. It's very, very cold. Dry ice is ice. It's like ice, okay? And what we have here is, look at that. I take it out, and especially on the nice black gloves, you can see it's already turning into gas. Now remember what that means. It means that it is sublimating. In order to change to a gas, we have to break the bonds between the molecules. So hopefully you'll see how strong I am, but dry ice, even though it's a solid, can be, see, it's just because the gloves are too big, can be broken, okay? So I can break it off quite easily, and then it starts to supplement. Now I wonder if I can break a better piece off. I'm just not very strong. No, hang on, wait, I can.
Can you?
No, I can't. We'll put that back in. We'll take one of these pieces because it'll be more fun. Okay. So what we have here is just because I'm a girl. All right.
Whatever, girls are actually strong.
Yeah, except in live national television. Okay. So, plain water. It's purple because I have universal indicator in there, and I've actually put a little bit of a base in there because I want you to see what happens. We're going to put the dry ice into the water, and look at that. Almost looks like the water's boiling.
Oh, that is so awesome.
Unfortunately, I don't know if you can hear. I'll be really quiet with my mic there. Can you hear it bubbling?
I can hear it from here, so
Yeah,
they should
so
hear
you
it.
can hear it bubbling, and it bubbles away. Now, doesn't that look like what you see on TV when they do the whole
Yeah, the
like
smoke
experiment, and they have the pan to like the scientist's lab, and then there's all this. This is all it is. Okay, that's really all it is. Now, hopefully, and I can take this off, you can see that the liquid at the bottom is changing color. That's because the carbon dioxide that's turning straight to a liquid, it's not even going into the liquid phase, and you can see it quite nicely in here, is that there's been solid in here for ages, and there's no liquid in there. It's still solid, and it's just coming off straight as a gas. It's sublimating. Now, it sublimates because actually the force is the intermolecular forces, the van der Waals forces in carbon dioxide are very, very weak. Okay, it's a linear molecule, so it's a straight molecule, nope, and it's non-polar. So it's very, very weak, very, very weak, okay? So it's easy to break it. Easy to see with this one. Now this is going to go for quite a while, and when we leave it, we'll come back to it just now, is what we'll actually see is, it'll be interesting to see what color this goes to. Now remember, this is what's in your fizzy cold drinks, by the way, in gas form. This is the gas that's in fizzy cold drinks. It's a bit scary, hey?
That is a bit scary.
It is a little, yeah. So we're going to leave our bubbling brew over there. Okay, now let's get on to viscosity. So what we're going to do is I have a whole bunch of liquids. I have water, I have cooking oil, I have glycerine, okay, we have some antifreeze, and we have a shampoo. Whole different bunch of liquids, and what we want to show you is viscosity. So the first thing I'm going to do is I'm going to pour my water, and you can see it runs quite easily into my test tube, nice and simple. And I want to pour quite a bit in because we're going to drop things into it just now. But that was fairly easy. Water isn't very viscous. It runs very, very, very easily, okay? The next one is cooking oil, okay? Ooh, so we're using the filter for two reasons. One, so I don't mess everywhere, which is always a good idea. And two, because we want you to be able to see how it runs. So we're going to put the cooking oil in, and we're going to see that it's not quite as fast. This one, ooh, like we said, so I don't mess everywhere, and then I proceed to mess everywhere. Okay. So we have, oh, and I've gone, no, there we go. So, yes, I'm messing everywhere.
That's okay.
This is why you should wear a lab coat. Do
and
not
some
learn
gloves
from this.
Maybe,
hey?
And a mask maybe, and some
well, maybe
gloves
not for this one, but a lab coat's good because, or have at least got paper towel. Anyway, you know what we're going to do? Now we're going to do the same with the glycerine. Okay, now glycerine is, hopefully you can see it actually runs slower than oil.
Slower and more slimy-ish.
It's absolutely, it's one of those things that you sort of go, yeah, I don't want anyway. It's good for your hair.
Yeah, don't some people put on their skins? And
I
their
believe
hair?
so. It's just a bit oily for me, hey?
Yeah, it's a bit oily.
But it's a nice natural product. So though it is the basis of glycerol, which is the basis of explosives, no, it's not going to explode. Okay.
Aww.
I know. That's exactly what my kids do in class as well. Oh, but man. Okay, so let's put some antifreeze in. I have no idea what this is going to do.
Isn't that going to be exciting? Because it might explode.
Well, it's actually quite runny, which is not what I expected.
A weird color, hey?
It is actually. I didn't know it was green. Anyway, now it looks all funny because there's oil in here, but don't worry about it. Now, antifreeze, remember, is what we put in our car so that the engine doesn't freeze up in winter. Okay, so it's a good thing to have. And then we've got some shampoo, okay, which we all know is quite an important thing to have. And this one's going to be fun because this will take a long time. Okay, and you can even see just by, this is the one that might take a little while, pouring it in, you can see it's all, it's definitely more viscous, it's more slimy, it takes a longer time, so we're more likely to have put too much. There we go, hopefully. Okay, well at least everything will smell nice today. Okay, so there's our, so now we've had an indication and we go, that's cool because we sort of saw how they poured. Now watch what happens. Now I've got a whole set of fun things, marbles. So this was the water, and unfortunately this, okay, you missed that completely. So let's try that again. That doesn't take too long.
Yeah,
okay, let's do the marble in this was the oil.
Okay.
Ooh, look at that.
Oh, that is slow.
Takes a long time because it's having to move. So that's definitely more viscous. This was the glycerine.
Yes.
So let's see what happens with the glycerine. Look at that.
Even slower.
Now that, I wouldn't have said it was that much slower than the oil, but actually it is quite a bit slower, which is quite interesting.
Yeah.
the antifreeze, and I'm actually very keen to see this one because I don't actually know what this one's going to do. That was sort of between the oil and the water. And then, of course, I think we all know what's going to happen with this one because this is the shampoo. So let's see what happens. Oh, my word, look at that.
Let's see if it ever goes down.
It might eventually, but if you look carefully, you can see that the glycerine, it's still busy. So if I had to put this in an order, I would probably go that the water was the least viscose, then it was the antifreeze, then the cooking oil, then the glycerine, and like you said, eventually
the shampoo.
In fact, I don't think it's going to go anywhere anytime soon.
Next Tuesday, maybe.
Yeah, next Tuesday we'll have a look and see what it's busy doing, okay? And over here, my dry ice is still busy going, but it's changed color. We might have made it a little bit too basic. And eventually it's got universal indicator in it, and this will go, it'll indicate that it's gone acidic. But I just need to wrap this up because unfortunately we're going to run out of time. But the viscosity, how slow it took for the marble to come down, shows me the strength of the intermolecular forces. So the shampoo, which I have no idea what the shampoo molecule is. Okay, remember every shampoo is different. I have no idea what this molecule is. But I know, I can say without a doubt that the intermolecular force between the molecules of this shampoo compared to water is much stronger. Which means also things like the shampoo will have a higher melting point. The shampoo will have a higher boiling point. Cooking oil has a higher melting point than water, has a higher boiling point than water, which is what makes it so dangerous, okay? In fact, cooking oil has a flash point. Cooking oil won't really boil. It'll burst into flames rather, okay? Glycerine, which I actually found quite interesting, sorry, this was the antifreeze, which to me actually makes a lot of sense that you don't want it to have a very low, you don't want it to melt at a very low, you don't want its forces to be too strong because you actually need it to stay a liquid, okay? So you want it to be able to melt at quite a low temperature. Otherwise, putting it in your car doesn't help us in winter because if it freezes at a low temp easily, then it's going to be useless in the car. The point is to stop the engine parts from freezing, okay? Your glycerine, which we know is quite a thick liquid, is quite nice, stronger than the cooking oil, which I found quite interesting. All right. I quite like this. So let's go back to the board. So we've done the dry ice in the water. We've also done the measuring cylinders. Now we did say put in a measuring cylinder. We used a test tube instead because it was just easier. Okay, so quick. And we're going to do this in like 2 seconds flat. There is a graph. It says, consider the following graph and explain the trend in the melting points of the compounds. Now, if you look here, H2O, H2S, and then it goes up, CH4, SiH4, these are all in the same group. But let's consider the first one with the water. Water has an unexpectedly high melting point compared to the rest in this trend. This is actually all in the same period. What that means for us is that water has a very, very strong intermolecular force. It's a special intermolecular force called hydrogen bonding. Very, very strong. If we go across, hydrogen sulfide, H2SE, H2TE, as we go across, these are becoming bigger and bigger molecules. The bigger the molecule is, the stronger the intermolecular force, the higher the melting point. Water is actually the smallest molecule out of all of those, has the smallest mass, but it has the highest melting point because its intermolecular forces are the strongest. Okay? Let's go to the last question. Explain why it's possible for a spider to walk on water. You've seen those little insects that run along the water. That's because water has surface tension. That surface tension is created because of the intermolecular forces between the water, okay? And because it's strong enough, the spider can run on top of the water because of the forces, okay? And unfortunately, I have run out of time, though I really hope we learned something today.
I think we did.
And I'll see you guys all next time.
Thank you, Tracy. Was that not absolutely cool, guys? I know Brian just said cool with many zeros. It was really awesome, guys. This is the kind of stuff that we do, and that's why we need you guys to join us every single week, guys. This is really helping you guys. I know that it is because you guys have told me that it is. So, great lesson. Thank you for joining us, guys. Please keep helping each other, keep learning more, keep learning extra, guys. Where would we be without you, and where would you be without us? So let's do this together, okay? Bye-bye, guys.
Physical properties of substances, okay? So now remember, physical properties are things like boiling point, melting point, all those sort of things. You spent a lot of time at the beginning of grade 10 discussing those things. And what we're going to look at is what actually determines those boiling points and melting points, and we're going to look at some trends, okay? So the first thing we need to do is let's go back and recap on some of the different types of chemical bonds. Now, chemical bonds are what we call intramolecular bonds, okay? So this, what we're doing first is intra, okay, with an A, not inter, intramolecular bonds. So what we're discussing for this first little bit is the bonds between the atoms, okay? So how the electrons are shared or given, or how they react with each other. It's the sharing or the giving of electrons. Now the first one is your covalent bond, okay? Covalent bond, this is really what we get into with shapes today. When two non-metals, or two or more non-metals, okay, bond together in a covalent bond, we get a bond together, it's a covalent bond, okay? What is it characterized? The electrons are shared between the two atoms. The electrons are shared between the electrons, between the atoms. Remember, the whole point of bonding is for our atoms to get a complete energy level. So if we look at something like chlorine, okay, and you remember from grade 10, you did Lewis notation. Remember, chlorine is in group 7. Okay, chlorine looks like this, has 7 valence electrons, and we go, well, over here, it has an empty space. In order for chlorine to get a full energy level, it needs another electron. If we bring along another chlorine, okay, this chlorine also has 7 valence electrons, and it also has an open space. So now what happens is these, let me just get rid of, where did it go? I just want to get rid of this part quickly. Now, what happens is these two electrons come together and say, well, we can share this space. Both chlorines want an electron really, really badly, but because they have the same electronegativity, in other words, they have the same force of attraction for that bond, for those electrons, they will share them, okay? So this becomes a shared pair. In this case, it's what we call a non-polar bond. All right, do you remember that from last year? It's completely equal sharing, non-polar, okay, which means neither of them tend to have the electron more than the other. If we look at hydrogen chloride, HCl, remember hydrogen only has one little electron, which it doesn't really want to give away. And then we have chlorine, okay, which has 7. So what happens is it'll bond like this. You remember this? Here's our bonding pair. That's what we call that. It's called a bonding pair. But there's not equal sharing. Now there's very unequal sharing. Chlorine actually has a high electronegativity. Remember that from last year? Electronegativity being the force of attraction for the bonding pair. Chlorine wants that electron so badly that what happens is this becomes what we call a polar bond. Okay? It's a polar bond. So the chlorine almost looks negative and the hydrogen almost looks positive, but not quite. We don't say it's become
Working off today, guys. Isn't that absolutely special? I know it is. Don't worry. Don't shout at the screen. I've got you. Jump onto that page, download them. You can highlight them. You can share them with your friends, your uncles, if they're doing grade 11 physical science, and your cousins and your friends, guys. It's going to be an awesome show, basically. So please join me on the page and join Tracy for such an awesome lesson. How are you, Tracy?
Good, and you?
Good, thank you.
I like that. Let's share with your uncle.
I think our uncles need some atomic combinations.
Hey, why not? Anyway, as Katlego said, we're doing atomic combinations today, and we're looking at molecular structure, and we are going to cover a lot of work today. So hold on to your seats, and I have got some fun stuff planned for near the end. We're going to make some things with marshmallows, which are all mine. anyway. So we're going to look at atomic combinations. What are we actually going to try to get through today? Well, we're going to identify and describe the shape of molecules. That's really important. We're going to discuss the concept of intermolecular forces. This is a very new concept for you guys. And then we're going to discuss how intermolecular forces affect the
Hello guys, welcome to Learn Extra Live. Today we are doing physical science, guys, for grade 11s. I hope you grade 11s are excited as I am, of course, for an awesome lesson. What we need to do today is that you guys need to jump onto our Facebook page, which is facebook.com/learnextra, and our Twitter handle is @learnextra. You guys need to ask as many questions as you can. Say as many things as you can, basically, guys, because nothing that you say will ever go unnoticed. I promise you, I'm seated here the entire lesson and I'm willing to answer every single one of your questions. Today we're with Tracy and we're doing atomic combinations, guys. So get out your worksheets and your workbooks and your textbooks and your pens and pencils, and also jump on to learnextralive.co.za/live for the notes that Tracy will be